Assalamu alaikum. Dear students, welcome to the lecture of the classical mechanics. In this lecture, we will be discuss the solution for the problem number 7.24, which says that consider a simple plane pendulum. Simple plane pendulum consisting of mass m attached to a string of length L as shown in the figure. This is the simple plane pendulum which has mass m and attached with the string which has length L. After the pendulum is set into motion, the length of the string is shortened at the rate dl over dt, which is equal to minus alpha and is equal to constant. Mean the length of this pendulum is shortening by constant amount, the constant rate, which is equal to minus alpha. The suspension point remain fixed. Mean this point is to be fixed. Compute the Lagrangian and Hamiltonian function. We have to find the Lagrange and Hamiltonian for the system. Compare the Hamiltonian and the total energies and discuss the conservation of the energy for the system. Then we will compare the Hamiltonian with the total energy. If this Hamiltonian is equal to the total energy of the system, mean that total energy will be remain constant. It means energy of the system will be remain conserved. Otherwise, if Hamiltonian and the total energy of the system does not becoming equal, so in this case our system will be non-conservative and it will dissipate energy at a constant amount. So let's go to solution. The first, we have a sample pendulum and it is in two dimension. This is the mass m and this is L, which depend upon t, and this length will be changing. L depend upon t because L is changing with time, dl over dt. So kinetic energy for this system will be equal to which will be equal to m over 2 L dot square plus L square and theta dot square. In this case, this L is going to be changed. Otherwise, this remain constant. But in this case, this length is going to be changed. Therefore, we have put a dot sign, and this term is also contributing in the kinetic energy. So kinetic energy will be equal to m over 2 L dot square plus L square theta dot square. Here, two variables are actually going to be changing. The first is the theta as a major angle, and the second is the length, which is going to change. So these two will play role in the kinetic energy. So m over 2 alpha dot square, alpha dot, you know that dl over dt is written as alpha L dot. So L dot is equal to alpha, so L dot square will be equal to alpha square, and plus L square theta dot square. This is the kinetic energy. And you know that potential energy, we can find the potential energy if we resolve this length into two components. The first will be L sine component and the second will be L cos component. And below the origin we have negative negative y-axis, so mu is equal to mgy, u will be equal to mgy, and y is minus L cos theta because this is in minus y direction. So y will be equal to minus L cos theta. So potential energy will be equal to mgy and y is minus L cos theta. So minus mg L cos theta. Thus we have find the kinetic energy and potential energy. Now go to what the Lagrangian. Lagrangian is equal to T minus U. And we have kinetic energy. Kinetic energy is this whole expression, m over 2 alpha square plus L square theta dot square. This is kinetic energy, and minus potential energy. So minus this minus sign and this minus sign will go to plus mgl cos of theta. Thus we have found the Lagrangian of the system. This is the Lagrangian of the system. Then the second requirement of the question was to find the Hamiltonian. We can find the Hamiltonian by this relation if we have Lagrangian. H is equal to P theta, theta dot minus L. This is the Hamilton equation and we can find the Hamiltonian. So you know that P theta is can be found by partial L over partial theta dot. So if we take the derivative of the found Lagrangian with respect to theta dot, this will give the value of P theta and we will then plug this value back to this equation and manipulating this will give the Hamiltonian of this system. So taking derivative of Lagrangian with respect to theta dot, this Lagrangian. So when we take the derivative and plug in this equation, it will give P theta dot square over 2 ml square minus m alpha square over 2 minus mgl cos of theta. And in this step, we have just take the derivative of Lagrangian with respect to theta and plug these values into this expression and also put the value of this Lagrangian here at this one. This is the value of Lagrangian and plug this. Okay, then this will give this whole expression. Okay, now we have to analyze this. The first thing is that this is the Hamiltonian of the system. This is the Hamiltonian of the system. So we have to compare this Hamiltonian with the total energy which should be equal to T plus U, because total energy is always equal to kinetic energy plus potential energy, and this is Hamiltonian. If we sum this kinetic energy plus this potential energy, this should be equal to this Hamiltonian if this is conservative. But if we sum this kinetic energy plus potential energy, this does not becoming equal to this Hamiltonian, which is different from the total energy T plus U. The total energy is not conserved in the system because work is done on the system and we have d over dt, mean total energy is not remaining constant. And this show that our system is not conservative. Some external force is going to be acting on the system. So these were the requirement of this question. I will stop at this point and meet in the next session.